All right, so like I told you yesterday, we're going to shift gears a little bit from solving the triangles like we have been. It's not that it's going away, okay, because it's going to show up inside of other things that we're doing, but we are shifting gears a little bit. So this is going on page 75 when we're done. We're going to talk about polygons. So even though I said we're shifting away from solving triangles, is a triangle a polygon? Yes. Can you give me other examples of polygons? A square, rectangle, a trapezoid, rhombus. A circle is not a polygon. Not like a hexagon, a pentagon, right? Polygons? Yeah. Not new to you, yes? My guess is, though, you probably have never seen the definition of a polygon because the definition's kind of weird. But we're going to take a minute to look at the definition because there's things about these weird ones especially that I want to make sure that you get. Not necessarily content-wise, but just structure-wise more than anything. So this is the definition of a polygon, which I know you know what it is. It's not new. It's not like it's a super complicated thing. But the definition makes it out to sound like it's a pretty complicated thing. It says a polygon is a closed plane figure. Okay, so first of all, the plane figure part of that just means that it's two-dimensional, formed by 3 or more segments, such that each segment intersects exactly 2 other segments, only at their endpoints, and no 2 segments with a common endpoint are collinear. Okay, so that's very wordy and kind of weird sounding for something that just could be a pentagon or a hexagon or whatever. And I know that you probably think that about a lot of things that we do. Like, why does it have to sound so complicated when it's so simple? But there are reasons for that, and that's what I want you to see here. First of all, collinear means what? On the same line. Collinear, on the same line. All right, so if I had if I drew this, would this be a polygon? No, it fails the definition right here because it's not closed, right? It is a plane figure with 3 or more segments and blah, 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 but it's not closed, so it's not a polygon. What about this as a whole? What do you think? Is it a closed plane figure? Yes. Is it formed by 3 or more segments? Yes. Such that each segment intersects exactly 2 other segments. Well, this segment right here only intersects 2, but look at this one. Does this segment right here intersect exactly 2 others? No, it intersects 3. It intersects this one, and that one. So right there is where it fails this definition. That's why we have to have something like this in here, because that's not a polygon, or that's not what we're trying to define. It also doesn't intersect it only at their endpoints, because these do, but this right here intersects in something that's not the endpoint, so it fails it there too. What if I had this? Is this a polygon? Yes, right? It's a 4-sided polygon. But what if I said, well, that's not really what I meant. What I meant was that it has 5 sides. Okay? So I built that with 5 line segments. Is it a closed plane figure? Yes. 3 or more segments? Yes. Intersect exactly 2 other segments? Yes. Only at their endpoints? Yes. Then it goes on to say, no 2 segments with a common endpoint are collinear. So these 2 segments here have this common endpoint, and they are collinear, right? Which means if I'm, as a 4-sided polygon, yes, this is a polygon. I can't say, well, I really meant it had 5 sides. This is not a 5-sided polygon. Does that make sense to you? Now, I do not think that any of you would think that this is a 5-sided polygon or be confused by these either. That's not why I went through all that. But I wanted to show you that we have to say what seems like way too much information in a definition, because if we don't say all of those things, then it would include these, and that's not our intention. Okay, so when you sometimes good definitions can be very short and to the point, but sometimes you got to throw in a lot of other stuff so it'll exclude things that you don't want. Okay, that's why sometimes they seem so crazy when they don't necessarily need to be. There's a reason for it. It's not just extra words. All right, so let's look at some other definitions that go along with it. So we're going to look at this polygon right here. So what would you classify this as by its number of sides? It's a pentagon, right? It's got 5 sides, so it's a pentagon. All right, so we're going to look at this pentagon, and so we have a blank of a polygon is a common endpoint of 2 sides. So here's 2 sides, BC and CE. This would be the common endpoint. What would you call this thing? You know what that's called. It's a vertex. Good. Then it says a blank of a polygon is a segment that connects any two non-consecutive vertices. All right, so we got to make sure we understand non-consecutive. In order to understand non-consecutive, you got to know what consecutive means. So what is consecutive? How could you? Not necessarily repeating, but like next to or one right after another. So like Monday, Tuesday, Wednesday is 3 consecutive days. Monday, Wednesday, Friday is 3 days, but they're not consecutive days because they're not in order. Does that make sense to you? So as far as vertices go, B and C are consecutive vertices. B and E are not. You see that? So non-consecutive vertices. So it can't be something like B and C, but it could be something like B and E. So basically it's talking about in this picture, the line segment that is line segment BD. This connects two non-consecutive vertices. What do you think you would call that thing? Starts with a D. A D. Y'all know what these are called. It's a type of line segment. Has 4 syllables. Diagonal. Diagonal. So diagonal. All right, so last period somebody asked me, said, well, what if it was like line segment, what if I connected A and C? Would that be a diagonal? Yeah, but he said, well, but it's not diagonal. Right, well, but it's the definition of a diagonal of a polygon. I know you think about a diagonal line like not being vertical or horizontal. A diagonal of a polygon can be, because the definition of what it is that it connects any two non-consecutive vertices. It doesn't matter how it's leaning, right? So yeah, they usually look diagonal as far as what you understand for diagonal to mean, but they don't necessarily have to. It's about connecting the vertices. Okay, we good? All right. So then it says, name a side, vertex, and diagonal in the polygon blank. So let's talk about how to name it before we start naming anything else. This is a pentagon. And if we named a triangle, let's just look at triangle BAD. If I named a triangle, I'd use my little triangle symbol and then put the 3 letters, right? We use the little symbols for some other polygons, but not all of them. If I want to name this pentagon, I'm not going to draw a little tiny pentagon because it probably wouldn't look like a pentagon anyway. Plus, the more sides you get, just the weirder it is. You just don't do that. So you would either, this is very generic to say polygon, or I could say pentagon, blah, blah, blah. It's probably better if it said pentagon, but I didn't type it out that way. So polygon, and then you're going to use the letters. Now with the triangle ABD, I could put them in any order as long as I wasn't saying things were congruent. But just like with triangles, if I'm going to talk about congruent pentagons, I got to make sure that my corresponding pieces line up. But if we're not worried about that, we have a lot of options on how to name it. We don't have just anything we want, but there are a lot. It doesn't matter which vertex I start with, and it doesn't matter which order I go in, or which order I go around in. But here's what I can't do. I can't say that it's polygon CBEAD. You see how I like zigzagged around? So you pick a starting point and you decide which way to go, and then you have to go around the figure in that, that way. But you could go CBADE, and I could say CEDABC. It's the same thing. It doesn't matter. Most of us would probably start with A anyway, because we just tend to start alphabetical. So I cannot go ABCDE, right? ABC, because it would jump over here, DE. So you have to go either, one way or the other. So we'll do ABC, and then it would have to be ED. So you just have to be a little bit more careful, because you can't jump around in a triangle, so we haven't had to worry about it, but it's not that big of a deal. All right, so we need to name a side, a vertex, and a diagonal. So when I go to name a side, what type of shape is the side, or what type of figure is a side of a polygon? A line segment. So when you go to name it, you got to make sure you name it like a line segment and not be sloppy with it. We've been doing this since August. You should be able to do this. So you got to have a little line segment symbol above it, right? And I have lots of options. This isn't hard. We're not going to name them all, but give me a side. Okay. So, well, I don't know. I heard AB the loudest. I heard other things, but they'll call them mixed together. We'll go with AB. So line segment AB. Any of them are fine. It's fine. Vertex. A. That works. And it's just a point, so I just name it like a point. A. What's the only diagonal that's drawn on here? BD. There are more that I could draw, but BD is the one that's on there. Okay, we all good? All right, so then we have a list over here, or a little chart where we can fill in the generic names of the polygons. What's the minimum number of sides I can have to be a polygon? 3, okay? because that's in the definition, right? 3 or more segments. Now 1 and 2 are on here because 3 is the minimum in Euclidean geometry. Remember we talked about the fact that the class that you're in is Euclidean geometry. There are more types of geometries, but if the average person just says, oh, geometry, we all think of the same thing. So even though I can't have a one-sided polygon, you can have a two-sided polygon in something that's a non-Euclidean geometry. We'll talk about that later. I'm really going to blow your mind at the end of all of this, having to fix everything else that you've been lied to about, and then I'm going to show you some different geometries. But for Euclidean geometry, we have to start with 3. So I'm going to give you a minute or so while I go check roll, and I want you to fill in as many of these as you can, because you should know them all. You should have already learned them. So don't ask me if you're right or wrong. Don't ask me what they are. We'll talk about that all together. I want you to be able to process through it a little bit first, and talk with people at your group, and then we'll talk through them, okay? If you think that it needs to be there, yeah. All right. 3-sided polygon, what is it? Triangle. Okay, then y'all said that with confidence. That's good. I used to give a quiz that basically looked like this chart, and you just like fill it in. And I had a friend that taught world geography, and she was like, hey, when you grade those, bring them to lunch and grade them, because they were freaking hilarious, some of the names that were on here, especially for 3. It'd be like a tritagon, a trigon, a threegon. Guys, don't try and make everything difficult. It's a triangle, okay? Okay, but then you have to be careful with 4. What's 4?
Square.
Oh, it's like a knife through my heart. Okay, listen, are squares and rectangles and trapezoids all 4-sided figures? Are all 4-sided figures squares? No. Okay, all 4-sided figures can be classified as quadrilaterals. Okay.
That's why I asked if you could put more than one, because
No. The name of the polygon. So that's if it's a 4-sided figure, it's a quadrilateral. Listen, there are special quadrilaterals, just like there are special triangles, but they're still all triangles, okay? And so all 4-sided figures are quadrilaterals. All 5-sided figures are pentagons. Okay, 6 would be hexagon. We're scared for 7. Okay. Okay, I got heptagon and septagon. Okay, those are the 2 things I get every time. Okay, both of them are very logical answers. It's not like a random thing you just made up. Okay, so who had septagon? Okay, so tell me why septagon. Because it sounds like 7. It's in French. Okay, because are you in French? How do you actually say 7? Sept, it's the same? Okay, I couldn't remember. I took 3 years of French in high school. I don't remember. Yeah, I could. Yeah, it's kind of, yeah, it has a little bit of a French accent. But basically, sept means 7, so it's a very logical answer. Those of you that said hepta, why?
hectagon.
Oh, hectagon.
You put that in front of covalent compounds, or when it's 2 of the same element. Maybe for 7, it would be
for 7, right? Okay. So, and I've had it kind of phrased that way a few times today. Well, in chemistry, we do this, so that's why I was thinking that. And one thing you need to understand in general for anything in school is y'all think very compartmentalized. Well, this was a science thing. This was a math thing. That a lot of times it's universal. You just happen to use it in that class, but it works for everything. Yes, ma'am. It is. It's a diagon. Well, it doesn't exist in Euclidean geometry, but it is, yes, for the same reason. All right, so although septagon and heptagon are both very logical answers, and I learned this today because I have not seen Finding Dory, that if an octopus loses a leg, it's called a septopus, I guess is what it's called. Something like that. Septipod, I'm not sure. But because that means 7, that's why somebody said septagon today. They were like, it was from Finding Dory. A very logical way to think. I haven't seen that movie. So anyway, even though they both do mean 7, for a 7-sided polygon, it is actually heptagon. So those prefixes and stuff that you're using in chemistry that you feel like this is a chemistry thing, and the reason you feel that way is probably because it's the first time you've actually used it, so all you have to relate it to is chemistry. Just know it works in everything. Yes, sir?
I wasn't sure if it was going to work that well, because for like quadrilateral, it could have also been like a tetralateral.
Yeah.
Or tetragon.
Could you call it?
A tetragon. Tetragon is kind of, Well, it's not a tetralateral. It would be a tetragon, and that is an acceptable way to say it. It's not the common way to say it, but for the same reason, it does work.
Triangle be trigon?
It technically can be trigon, yeah. But those were just wild guesses when people get, but it was more like tritagon and all weird things. But all right, what about 8? Octagon. And I heard it's octa. It is with an A, not octo. An octopus, right? Because really you don't always use all of the parts of the prefix, but you're right, it is an octopus. Probably because the O has something to do with how else the word is built. Because all of these, y'all talked about prefixes and suffixes in English for years, right? And then you do have these like specific ones that come up over and over again, but it's how words are built. And if you have ever spent any time actually like truly studying for a spelling bee, like, the weird, crazy words, you learn, not that I have, but I do know this, you learn how words are built and what the different pieces mean so that if you hear something, you kind of know what it should mean and how it should work. It's the same idea, is that these little pieces mean different things. All right, what about 9? And that's not what you said. What did you say? That it wasn't Nonagon. I don't know, but you were right. I wish you'd remember. No. Oh, I thought you said something else. If that's what you said, then no, you weren't right. All right. It is and I don't think it's nano. It's not nano in chemistry.
Nano is chemistry.
Nano is 10 to the negative 9.
Are you? But it's NA. Is how you spell it?
It's NA.
Well, somebody pulled out their chemistry notes and had something different.
There's milli, nano.
Look, do you have like your little list of prefixes? Because he read it off. Because somebody else said that earlier.
I got the prefixes from biology. It's so weird.
Okay, so somebody said nano earlier, and I don't know exactly what y'all talk about. And there are different ways to use some of these, but then somebody else said it differently and literally had his chemistry stuff out. So I thought maybe.
But what's 10 to the 9, not 10 to the 9?
Yeah, that's why it's to the 9.
10 to the 9 is giga.
Oh no. But don't you have like prefixes somewhere, like a list of them?
Yeah, yeah. What's
I have giga is 10 to the 9, mega is 10
Okay, yeah, but stop. That's because the mega, whatever 10 to the 10th is, however many zeros, that's why it's the mega. The mega doesn't mean 10. It's okay. It's okay. Oh, okay. Do you have it, Daniel? Look at you. I'm going to tell your chemistry teachers, look at them with their notes. Like, oh, never mind, I don't have it. Never mind, I thought I had it, I don't have it.
You know what? I bet I got this. Here's my beautiful chemistry notebook.
Say,
This is from left.
So it's 1 mono, 2 di, 3 tri, 4 tetra, 5 penta, 6 hecta, 7 hepta, 8 octa, 9 nano, N-O-N-A.
yes, it's nana, not nano.
Yeah.
N-O-N-A. That's what I thought. Y'all are saying it wrong because either.
Also, it's Nana. Oh, yeah.
Good job, Abel. Okay, that's why I was curious as to like, did he have it written down wrong? I think y'all were just nano probably makes more sense to you because of like words you've heard, but it's nana. It's not nano. It's a nonagon, yeah. So 10 is decagon. How many years are in a decade? 10. How many meters are in a decimeter? 10. It all relates. They're not all even from the same subject or concept, but deca or deci or deca mean 10. So that's kind of how either the A or the I, depending on what's going on with the word. No, because it's deca. Because that's how you piece them together. That's like the connector. Does that make sense? And that for that concept, that's the connector. So the I would be like a concept otherwise. And at decimal, you have the tenths, and then it goes up by tens, right? Hundreds, thousands, so forth. There you go. Decimal. All right. Then, so as far as your chemistry stuff, that's when the kid closed his book. He was like, that's as far as I can help you. So then we get to 11. Remember, all these are they're built. They're not just random words that people made up. When we start counting in English anyway, when you get to 20, it's like 20 and 21, 22, and then once you understand that concept and you know what 30 and 40 is, you can count on for like ever. So it's like 20 plus 1 and 20 plus 2. Same concept here, except we're starting with 10. So it's like 10 plus 1 and 10 plus 2 and so forth. So how do you say 1 in Spanish? Uno. How do you say 1 in French? Un, good. It's like un, and I think is it U-N-E is how you spell it? Okay, but it sounds like you're just using the UN. So those words are very close to each other because they're both Romanic languages, so they're very close. But we don't use the whole piece, we just use the first two, so this is an undecagon. Okay.
So would 12 be die?
Okay, 12 is not die, even though die does mean two, close. It's close, but it's a dodecagon, yeah.
Why does it? I put never mind. I don't know how to.
Okay. So you got an undecagon, you got a dodecagon, and then a tridecagon. It's and so there are names past 12 up to infinity. You are not expected to know them past 12. I am going to show them to you. Obviously, I'm not going to give you an infinite amount of words because that's impossible. However, there are some examples of how to build them and like the pieces you need to build them. I used to have shapes hanging from my ceiling that had some crazy names, and I used them for teaching purposes, kept referring to them as decorations. Well, apparently they're breaking fire code, and I've been breaking it for like 20 years, but nobody ever said anything, so whatever. But they were like, and how do you, well, if you want to put your decorations back up, I said, they are not decorations. I use them for teaching purposes, because I can't really put three-dimensional figures on the wall. But anyway, we look at the names, and I'm going to get them hung back up legally, now that somebody finally told me how to even do that. No, it has to do with what it's hung by. Whatever. What has to be a specific kind of metal or whatever. But I mean, honestly, if the shapes on my ceiling are our downfall, we got a lot bigger problems. But anyway, but those words there, they're all built with something. You're not expected to know anything past 12. So just for common use, because some of the names are kind of crazy, but for common use, we have names up to 12. And then if we have n number of sides, this just becomes an n-gon. And it's not an n-agon, even though the rest of them have an a in there. So for instance, if I have a 25-sided figure, yes, it has a crazy name that goes with it, but we would just call it a 25-gon. Okay. And just, a 13, even though it would be a tridecagon, we just call it a 13-gon, a 14-gon. And it's kind of real obvious how many sides it has. Okay, we good with that? All right. So here it says, is the figure a polygon? If yes, then name the polygon by the number of sides. So is this a polygon?
Yes.
Yes. And what would we call it? A hexagon. What about the second one? No, I already kind of talked about that one. What about this one? Yes, it satisfies everything in that definition. How many sides does it have? 12. So this would be a dodecagon. And somebody earlier today said, I've heard of a dodecahedron. Is that like the same thing? Okay, no, it's not. A polygon is a two-dimensional figure. A polyhedron is a three-dimensional figure, like even just a prism or whatever is a polyhedron. And those were the things that I had hanging. Right now, we're only talking 2 dimensions. We'll get back into 3-dimensional stuff later, but everything for right now is 2-dimensional. So the polygon, we're talking about how many sides. Polyhedron, it's how many faces. So a dodecahedron, that still does mean 12, but it means it has 12 faces, or 12 polygons make it up. Where here, this is just the 12 sides make it up. All right. Then on to the next part of this definition. This, super important. Easy word, but because it's kind of an easy common word just used in here, sometimes you gloss over it when you read things, but it's very important because it tells you that the polygon is equilateral and equiangular. So what does it mean to be equilateral? Congruent, good. All sides are congruent. Equiangular means all angles are congruent, okay? And remember, for a triangle, if you're one, you're the other. You can't be equilateral and not equiangular. You have to be both if you're a triangle. For any other polygon, you can be one and not the other. So this refers to what happens when it's both. For instance, a rhombus that's not a square is equilateral but not equiangular. A rectangle that's not a square is equiangular but not equilateral. Does that make sense? And then that works for any of the rest of them. But if it's both, then it is a regular polygon. So yes, a square is a regular polygon because it is equilateral and equiangular. The other regular polygons, just to kind of give you an idea, is that it's the ones that if you walked into a kindergarten classroom and they were just learning their shapes, there'd be the ones that you see on the wall. There'd be the ones that you could draw in a template, things like that. The ones you think of when I say picture an octagon, you're probably picturing something that looks like a stop sign, right? And not some other weird shape, which would still have 8 sides. Right, a trapezoid's not a regular polygon, okay? We're good with that? That's all it means. But equilateral and equiangle, that's important because when it just says, hey, this is a regular polygon, a lot of times these are the things you need to know are true to be able to do what you need to do. And if you don't even know what regular means, that's a problem. All right, so then there's 2 other ways to classify them. The first one, it says it means any part of a diagonal contains points in the exterior of the polygon. So if I look at this polygon right here and I draw in a diagonal, now I could draw in the other ones, I'm not going to draw them all in, but is it possible for me to draw a diagonal in that polygon and have any of the points of the diagonal on the outside of the polygon, or would they all be inside? They'd all be inside, right? No matter which one I drew, everything's inside, right? If I look at this one, I can draw this diagonal, all the points still inside. But if I connect these 2 vertices, I get points outside. Does that make sense? And that's what it means here by any part of the diagonal has points in the exterior. And it also looks like it's caved in. This is called a concave polygon. Concave means any part of the diagonal contains points in the exterior. Then when no diagonal contains points in the exterior, that's more like this. When I draw the diagonals, everything's on the inside. This is convex. When have you heard these words before together? Science. With lenses, which is like 6th or 7th grade, you talk about concave and convex lenses. Mirrors as well, and it's like when you're talking about light refraction and things like that. But anyway, it's not exactly the same thing, but the words are used because they have commonalities anyway. But concave looks like it's caved in or dented in. Convex looks has all the vertices poking out and it looks kind of ballooned out or whatever. But so they're easy to figure out kind of by looking, but if you ever get confused, the actual definition talks about the diagonals. Okay, we good? All right, so let's look at these. It says tell if the polygon is regular or irregular. Tell if it's concave or convex. All right, so is this regular or irregular? Okay. Is it equiangular? Yes. Is it equilateral? No. So it is irregular. It has to be equilateral and equiangular to be regular. We good? Concave or convex? Convex. Okay. All right, so this second one, regular or irregular? Regular. It is equilateral and equiangular, so it is regular. Concave or convex? Convex. Okay, good. All right. C, regular or irregular? Okay. What is it? What would you name it? Okay, it's an octagon. Is it equilateral? Yep. Is it equiangular? How many angles does an octagon have? 8. Are all 8 angles congruent to each other? No. Right. See, you have these 4 angles congruent and these 4 angles congruent, but all 8 angles are not congruent. So although it's symmetric and it kind of looks pretty, if I said draw an octagon, would this be your first instinct to draw something like that? No, your first instinct would probably be to draw something that looks sort of like a stop sign. Yes? So remember, those are the actual original ones that are all poking out. Those are the regular figures. And this is not regular because we can't say that it's equiangular, so it is irregular. Is it concave or convex? Concave. All right, so here's a little hint. If a polygon is concave, it can't be regular. So if it's concave, it's automatically irregular. So that's another way if you're getting confused with it. If it's convex, then you have to check because it could be either one. But if it's concave, it's automatically irregular. No questions asked. We good? All right, awesome. Alrighty, so it says, to find the sum of the interior angle measures of a convex polygon, draw all possible diagonals from one vertex of the polygon. Now, it doesn't say draw all possible diagonals and stop there. It says from one vertex of the polygon. So you pick one vertex, it doesn't matter which one. I'm going to pick this one. And then I'm going to draw all the diagonals from that vertex. Can I draw any diagonals in a triangle? No, because you have to connect non-consecutive vertices, and those don't even exist. So I can't even draw a diagonal there. But I can move on to the quadrilateral. And then I can, from this vertex, I'm going to draw this diagonal. Now, it is possible to draw more diagonals, but again, I'm not drawing all of them. It's all of them from one vertex, and that's the best I can do. Okay? And hang on a second. I'm sorry. So then Pentagon, I'm going to pick this vertex. I'm going to draw, I can draw that diagonal and that one, and then that's the most I can do. Hexagon, that one, that one, that one. Okay? Does that make sense? Then there's a reason we're doing that, but that's what it asked me to do. All right, so then I'm going to look at this little chart here. And for these are the polygons that we have up there. For the triangle, we know it has 3 sides. Your quadrilateral has how many? 4, 5, 6, and
infinity. Oh, 13 and above.
right.
Whatever it is.
Right. How do I represent that?
Oh,
N. Okay. And N-gon has N sides, so whatever N is. All right, so then I look at, after I drew in those diagonals, how many triangles did I get? Well, with the triangle, I got 1. With the quadrilateral, I got 2. Pentagon, I got 3. Hexagon, 4. N-gon, is it N? I don't think so. Look at what's happening here.
1, 2, 3, 4, 5. What?
Be what? N minus 2.
Wait, why? Because
3 minus 2 is 1, 4 minus 2 is 2, 5 minus 2 is 3, 6 minus 2 is 4, so N, and then N minus 2. You may have, sometimes this like was part of intermediate school and then it wasn't, and I don't know if, I don't even know. It might be one of those optional things. Sometimes I'm not sure about that. But the patterning here, you know what, you might have seen it in when you were doing patterns to look at and write equations. It's probably come up, this was probably like an example when you were trying to write equations and you were looking at patterns in this to be able to come up with it with a variable. That would be a good like example for that. It may not have gone any farther to really explain to you what the heck you were doing and why, but yeah, you may have seen it before. All right, so we did all this for a reason. We know that there are how many degrees in a triangle? How many total degrees? 180. 3 angles, but yes, 180. How many total degrees in a quadrilateral? 360, okay? And then past that, you're not expected to just know it, but it does increase. So you need to know not all polygons have 180 degrees. So I got 1 triangle here. The 2 triangles here, that's where your 360 actually comes from, okay? Because there's 180 degrees here and 180. So if you look at how many triangles we get, well, when you have 1 triangle, it's 180. When you have 2 triangles, it's 360. For the pentagon, we get 3, so 3 times 180, there's 540 degrees in a pentagon. Hexagon, I get 4 triangles, so 4 times 180 is 720. Does that make sense? And then what would go right here? N minus 2. Okay. So if I had a 25 gon and I wanted to know the total number of interior degrees, do I multiply 180 times 25? 25 minus 2. Good. So it'd be like 23 times 180. And that'd be a really, really big number, right? The more sides you get, the more angles you get, and the angles get bigger. So as the number, not only do the number of angles increase, but the size of the angle increases as well. So if you think about a 25 gon, unless it's drawn really huge, if it's drawn on even just a piece of paper, it's going to look kind of circular. And the more sides you get, the more circular it's going to look. It'll never actually become a circle, but the angle opens up more and more and gets closer and closer to 180. And so you get a number that's pretty close to 180 times the number of sides to get however many they're there. You can get really, really big numbers. But this is how we find this, because you're not expected necessarily even to memorize these. Some of them you kind of start to learn if they come up a lot, but it's okay if you don't know them. You just have to know how to find them. You could even use it for a quadrilateral if you had to. Hopefully you don't have to, but you know. All right, so this is your polygon angle sum theorem. So the sum of the interior angle measures, because we are going to talk about exterior angles tomorrow as well, but the sum of the interior angle measures of a convex polygon, it only works when it's convex, with insides is n minus 2 times 180. Now, if you just glance down at the next 4 questions, they're all pretty short. They all kind of look similar, have the same kind of words in them, but they don't all say the exact same thing. So these questions are short, they're simple, there's nothing complicated about this, but if you don't pay attention to exactly what it says, it's really easy to do the wrong thing. Most likely you're not going to miss it because you don't understand it. Most likely if you miss one, it's going to be because you didn't really read the question or do what it said. So we want to make sure we pay attention to these words. It says find the sum, that's an important word, of the interior angle measures, even though we only know interior at this point, of a convex octagon. All right, so octagon means that n equals what? 8. All right, so then that means, and since I want the sum of the interior, I get that from n minus 2 times 180. So that's 8 minus 2 times 180, which is 6 times 180. Now, I know if you were doing this at home, you'd be using a calculator, and I get that. But one of the things that I want you to really try and cut the cord from that calculator. And not necessarily 100%. I'm not saying never ever use it. I'm saying the more you think through things and understand how things are related, the better off you're going to be in the end. Yeah, you can straight up multiply this, and that's fine. But if you also already know some stuff, you can use some of the stuff that you know to help you with this. I want 6 times 180. If I know what 3 times 180 is, wouldn't I be able to just double it? Because that's basically like 2 times 3 times 180. 3 times 180 is 540. So it would be 1080. Now, you're not always going to have this right here in front of you, but that's, again, how I show you sometimes to split up your multiplication, you know, multiply by 3, by 2, or whatever. Learn how to do that. That's really going to be, like, for real, an important skill to help simplify things. It may not help you get a, you know, better grade on whatever, or help you be like a calculus genius, but it will help you minimize the stress on some questions when you can reason through things quicker like that. So this is the sum of the interior angles, and that's it. There's a lot of degrees in an octagon. So we look at B. B says pretty much the same thing. Sum, interior angle measures, convex heptagon. So n equals what? 7. So this is going to be 7 minus 2. Okay, so without straight up multiplying, which sometimes we might have to do, but can I use this answer to help me with this one? Subtract 180. This is 6 180s. I really only want 5. So if I take 1 away, that's pretty easy. That gives me what? 900. That is the sum of the interior angles. Everybody good with that? Now, does C ask you to do the exact same thing? No. It says the measure of each interior angle of a regular nonagon. Okay, so first of all, if it's a nonagon, n equals what? 9. All right, and then what else besides the fact that it says each and not some and it's a nonagon? How else is it different from B? It says regular, right? This says convex, this says regular. Well, our n minus 2 times 180 only works if it's convex. If it's regular, is it convex? Yes, it has to be. Because remember, if it's concave, it's automatically irregular. So if it's regular, that means it has to be convex. It doesn't work both ways. Like, not every convex polygon is regular, but every regular polygon is convex. It always will be, because it's the nice, pretty stop sign looking stuff. So it's convex, so it works. Now, it doesn't ask me for the sum. It asks me for each one. But in order for me to find that, I still have to know what the sum is. So I have to find it regardless of whether or not that's my final answer. So I still have to do n minus 2 times 180. So 9 minus 2 times 180 is going to give me 7 times 180. Right? Well, look, this is 5 180s. I need 2 more. What's 2 times 180? 2, what's 2 times 180? 360. Okay, so this is 5 times 180. I need 2 more 180s to be able to get this, right? So can't I just take this answer here and add 360 to it? It's 1260. So that is the sum. Is that my final answer? No, because that's not what it asked me for. So what can I do to find each one? Okay, can I divide by 9? I can only do that if all the angles are the same. Are they the same? Because it's regular. Good. Here, if I'd have changed just the beginning part of this and said the measure of each angle in a convex heptagon, I could not take that and just divide by 7. Because it might be regular, but I don't know. So if it's not regular, I can't just divide. I might have to do something else. But this is regular, so I can just take this 1260, divide by the number of sides, which is 9. And I know a lot of you aren't going to actually write this out, or even this part, because you're stubborn and you don't think you need to. But in that case, then what a lot of you are going to do is divide by 7, because that's the number you see, and then get 180 and think that's the right answer. So be careful. Make sure you actually divide by the number of sides. So 9 goes into 12 once, with 3 left over. Then 9 goes into 36 4 times, and then you got the 0. So that is each interior angle. Okay. Everybody good? All right. So, measure of each interior angle of a regular decagon. So what does n equal? 10. So I get 10 minus 2 times 180. That's equal to 8 times 180. Well, that's just 180 more than that. Yeah. So what's that? Good. 1,440. Or you could take the 4 times 180 and double it. Do that as well. And that is equal to the sum. Not my final answer, right? So 1440. Then I do what? Divide by 10, and that gives me 144. Okay, good. And we will start here tomorrow. Have a great day.